Wanted to quickly advertise the Argonne training program on exascale computing. This is a 2-week-long summer school, essentially, for high-performance computing, where you'll be introduced to programming for high-performance computers, parallel programming. There will be a section on artificial intelligence. It will be very similar to some of our early content, at least for the artificial intelligence. But if you're interested in, the broader topic of high-performance computing, being able to profile codes, being able to parallelize algorithms, it's a nice resource, especially for graduate students. So I just wanted to advertise that. Was also pointed out that we are aware of 2 current internship opportunities. There are actually more available via things like our SULI program, but these in particular were related to computing and AI, and you can find those at anl.gov/education. And then with that, we will get started. I think I will hand it over to Ben for introductions, but we've got a group here today. They're going to talk about fair data practices in the sense of AI. This is really focused on how do you provide people access to trained models, training data, essentially being able to reproduce results that you've either published or research that you've done, so that it's preserved and open for other people to use. So take it away, Ben.
Okay, can everybody hear me okay?
Yes.
Okay. Yeah, so thanks for the introduction, Taylor, first of all, and thanks for the invite to speak here, especially from Eli Huerta, who invited us. I think the title on the website was actually something along the lines of fair models or fair AI, and we sort of expanded the scope a little bit in the last couple of weeks to really think about the reproducibility aspect of sort of all of the different aspects between how you actually work with your code, your models, your data, your notebooks, all sorts of things like that. And so we'll have speakers that talk about each of those topics today. First of all, I want to say thank you to all of the people who have contributed. You'll hear from a number of them today. You'll hear from KJ and Ari and Logan, but also thank you to the group who's worked on many of the services that we'll talk about. Also our collaborators, people at the ALCF, APS, and more. Globus, of course, Globus Labs, NIST, TriMad for funding much of the data side of the efforts, and collaborators at 3M and other support from NSF. So with that, we'll show the timeline for today. So we'll start with a quick introduction and background. There is a little bit of setup as far as making sure you have accounts and things like that. So we'll walk through that very, very briefly. Hopefully some of you have already created Globus accounts in the past, but if not, we'll walk through that quickly. We have a document set up for materials and notes. I saw there was also a GitHub repository that's passed around that has all of the code and notes, so that's great. If you want more freeform notes, we have this bit.ly AI for Science -training 10. That's a Google Doc that will have some links and kind of a running tally of what's going on. And of course, you can also use Slack. As I'm in presenter mode, I can't actually see Slack very well, so I may not see it, but if somebody sees something there, please pipe up. So the timeline will look like this. As I mentioned, we'll have this introduction and background section. We'll then have a talk by Logan Ward on reproducibility and computational research. He'll talk about how to effectively use notebooks in the flow of creating your ML models and some best practices there. Logan is a scientist at Argonne. I'll give a talk on realizing fair data and model approaches in material science especially, but with an eye towards other sciences. I'm a researcher at the University of Chicago and Argonne. We'll then hear from Nikil, Ravi from the University of Illinois on his use of containers for AI models and TensorRT for inference optimization. And then we'll turn it over to Ari and KJ, who are both scientists at the University of Chicago and Argonne. And they will discuss this new capability called Foundry, which I'll talk about in my first section, and then they will show you some live demos. And we'll also talk about DL Hub, which is the data and learning hub for science, which is a way to publish your models that we are still working on at this point, but we wanted to give you a sneak peek of how that's going and what that could become. And then at the end, we'll have questions and flex time for discussions. So with that, let's start thinking about what we need to do for setup. So I will show you how to create a Globus account first. If I can figure out how to stop sharing my screen. Okay, it's on the other one. Sorry about that. So while I'm trying to figure this out, you can go to www.globus.org. Pause. There we go. Okay, so hopefully you can see the screen more generally now. I'm going to go to globus.org. Actually, I'm going to create a private window first. But basically, you'll want to create an account at globus.org. That's what we use for authentication in most of our services. It's free. You just go to globus.org, click login, and it will take you to this page that shows you various institutional and organizational logins. You can log in with Google if you prefer, Orchid. And if you don't want to do any of those, you don't want to use like your UChicago ID or any of those, then you can create a Globus ID. It's not capturing my typing very well, but there you go. So you could sign up with any of your institutional credentials, Google, Orchid, etc. And so we'll use that later on to authenticate to some of the services that we have. We also will be using collab.google.org. Google.com, sorry, Collab. Collab.research.google.com. So if you want to take a minute while we're going through some of the talks at the outset here to make sure that you're signed in for Collab, and it's a way to run notebooks on some cloud resources that Google provides, and we have some examples that we'll run through there. Okay, so I think that's the big part for the setup. We also have a GitHub repository that has collected examples. You'll see that in the Google Doc that I mentioned. We'll get back to sharing my screen. But today we'll talk about the fair data principle. So you'll hear this quite a bit today. And so I wanted to make sure that we define that. First of all, FAIR is an acronym for findable, accessible, interoperable, and reusable. FAIR is a set of principles to really help make data as useful as possible to the community. And you can find some detailed information about FAIR here, but most of these are fairly, no pun intended, fairly well described by the term, but we do have some specific data principles that are listed here, and we have some more quantitative ways to think about them and some subcategories. So I want to just walk through these. So findable might mean that metadata are assigned a globally unique and persistent identifier, so something like a DOI. Data are described with rich metadata. Of course, some of these are hard to define fully. Rich metadata means different things for different domains and also depending on the use. Metadata clearly and explicitly include the identifier of the data it describes. Good, so it's self-referential. Metadata are described or are registered or indexed in a searchable resource. So you should be able to find them by things like Google Scholar or domain-specific searching capabilities. The A is around accessible. So the metadata are retrievable by their identifier. So the identifier that you've created to make it findable, you should be able to access it with that. The protocol is open, free, and universally implementable. The protocol allows for an authentication and authorization procedure where necessary. Metadata are accessible even when the data are no longer available. So this is around once you create this unique identifier, you're meant to keep the metadata around for a long time in case somebody had used it in their analysis. People would be able to then use that same DOI, which is a number that you may see associated with journal publications. If you've like this number up here, this 10.1038/S data, that's a DOI. So people should be able to use that to find the data. And even if the data are gone, so it may be a terabyte of data was sitting there at one point, but in the future it's gone, you still need the metadata there so that people can understand that this was changed. The data should be interoperable. Metadata use a formal, accessible, shared, and broadly applicable language for knowledge representation. Metadata use vocabularies that follow FAIR principles, so the vocabularies themselves are fair. Metadata include qualified references to other metadata. And then reusable, where metadata are richly described with a plurality of accurate and relevant attributes. Metadata are released with a clear and accessible data usage license, so licenses are important. Metadata are associated with detailed provenance, and metadata meet domain relevant community standards. So there's lots of things kind of within each of these, and we'll talk about some of these as they apply to the different services that we have. So why is FAIR important? FAIR promises to allow researchers to seamlessly find and reuse data artifacts. It promises to enable building upon existing trustworthy data rather than starting over, which is always great. But why is FAIR not enough? FAIR by itself is, as you've seen, kind of a set of guiding principles at a high level. It's not really a distinct implementation. And so we need to show and create direct implementations of FAIR and computable data and models in various domains. And we'll discuss some of those today. And so with that, I'm going to turn it over to Logan Ward, who's going to talk a little bit about FAIR data and his approaches.
All right, thank you, Ben. And I'm going to get the screen share functioning so that well, you can hopefully see everything. Is everyone seeing a PowerPoint slide? Excellent. So we'll get started. So the bit I'm going to go through the talk today is giving some motivation for why FAIR research practices are important and how you can go about constructing your work such that making it reproducible is a natural consequence of the work rather than something you have to do after completing it and invest a lot of time into. So before I get started on that, you're going to hear a lot of my opinions on kind of effective ways of doing research. So in order to give you an idea of where I'm coming from, so you can decide how much of it you want to believe or not, I'll give you some background on what I've done as a scientist. So I'm a materials engineer by training. I did most of my work through my PhD on studying complex materials like metallic glasses and figuring out ways of using machine learning to avoid using the kind of atom scale modeling techniques that can cost thousands of CPU hours and in some ways require the use of facilities such as ALCF. Now, beyond all of this research background, I've been working with Ben and others at the University of Chicago for about 6 years now to study ways that we can make open science more accessible to the graduate researcher. So this hopefully gives you some picture of my research pedigree, but of all of this, I think the most important criterion here is that I've been doing machine learning research for a while, which has given me an opportunity to make plenty of mistakes, some of which you're going to hear about today, and will hopefully give you motivation for illustrating how the kind of practices I'm talking about will give you a leg up on ensuring that your research is easy to do and easy for others to recreate later. So with that, we'll talk at a very high level about why reproducibility in computational science is a problem. And I'll start off by pointing to some papers from close on 30 years ago. that described that machine learning was a difficult, or sorry, not machine learning, state that computational science is something that typical types of publications don't really enable. Now, this was stated relatively strongly by Buckide and Donahoe in 1995, saying that a scientific article about computational science is merely advertising, and that instead it's the software that's actually what enables later scientific developments. Green in 2003 stated that a refereed journal article is no longer adequate to describe computational science. Now, this is something that goes back 30 years, and it has been echoed through many other people in the community, because computational science, by its very nature, is something that should be intrinsically reproducible. Every bit of what you do in your science is broken down to one of the dumbest machines humanity has ever created and executed in the precise way that you define it to. So while this is a very bold statement, it's not entirely true. Algorithms themselves are random, so you may need to ensure that your work is reproducible by keeping track of the actual run files. And it's worth noting that computers, by their nature, don't record every bit of data they process. So those kind of intermediate results that are critical to capturing what happened when you performed a simulation are things you have to go out and intentionally develop. So in short, your role goes beyond just being able to tell the computer what to do, but as a computational scientist, you need to take time to record what was done exactly, what was the software that you wrote on it, and why you did this so that other humans can understand and extend your work. And so given these very high-level arguments and calls back to papers from the 90s, you may be wondering, why is this something that people have been complaining about for 30 years? And why is it something we're still talking about today in one of the AI for Science tutorial series? And that, as I've alluded to, is that computation or being able to reproduce science is something that takes intention. Now, if you're coming from an experimental background, this likely took the form of your laboratory assignments, training you to keep a laboratory notebook in which you keep track of all of your experiments. And if you do that well enough, and you're, I suppose, a lucky and skilled enough scientist, a diligent lab notebook is something that people can go back to and trace the exact moment where you discovered a particular phenomenon. This example here is one of my favorites. It comes from materials engineering. This is a lab notebook of Schmidt, one of the Nobel Prize winners, and they see a interesting mark in his notebook, tenfold, which is a type of symmetry that was thought to be impossible in crystals, yet he discovered it. And you can see his surprise in the laboratory notebook. And while this notion of keeping a good laboratory record is something that's praised across science, it's not something that computers make it natural to do. It's easy to have a mess on a computer that nobody knows about. So in short, being able to do computational science effectively requires taking the same kind of skills that you may have learned in undergraduate laboratory efforts and applying that kind of diligence to how you do your research on a software system. And today we're going to talk about the ways that you can use existing tools, such as the ones my colleagues Ben, KJ, and Ari are going to talk about later. But before we get into the work we've done on creating tools at Argonne and UChicago, I'll talk first about how widely used tools within the data science community can be used effectively to help ensure your science is reproducible and to be able to do that without much additional work on your end. And as you may have seen through many of these other tutorial series, Jupyter Notebooks are a great venue for being able to explain computational science in a way that others can understand it. So Jupyter Notebooks, speaking broadly, if this is your first encounter with them, are a way of writing software that allows you to interleave the actual compute code with well-formatted text and images that describe what is happening. Now, this is a technique that finds its roots in the software package Mathematica. If you're interested in science history or just enjoy reading in general, I recommend this article from The Atlantic from a couple years ago, where they make the bold claim, and one I still don't agree with, that the scientific paper is dead, that the way people are going to communicate science in the future is by publishing these sort of mixed documents like Jupyter notebooks that actually contain the methods in which to reproduce that science. Now, I think that's a little far-fetched, but I do think that Jupyter notebooks are a wonderful tool for you to be able to not only create versions of your software that are teachable, but also a means for being able to do your software or do your science the first time as a way that can be shared with others. So to demonstrate, we'll walk through the ways that I use Jupyter to organize my software. Through this lecture series, you've already seen how you can use it to run on remote systems, even powerful GPU nodes available at ALCF. And I'll explain how I use them intentionally to ensure that my research is kept reproducible and easy to communicate. And the short version of all of that is I write my notebooks in the same way that I write a scientific paper. I start with a title and abstract at the top. What is this notebook about? And what am I going to show you in terms of results? Then, and we're going to stretch the metaphor of paper, so bear with me. It follows with a related work section where I import libraries and data that are necessary to do the next steps. Then I have a series of, and apologies for this belabored metaphor, a series of paragraphs that start with a common theme. I introduce what I'm going to try to convince you of. I'm going to illustrate the evidence that supports that. Then I'm going to display a figure or something else that reminds you what it is that I was trying to prove and summarizes the evidence about it. So what we end up having in these notebooks are a series of these paragraph-like blocks where they follow that pattern of tell them what you're going to tell them, show them the evidence, and then remind them what you told them. So in short, this particular example from a study that I've been working on for a couple years on predicting how radiation particles are slowed down by materials illustrates how I performed a test where I wanted to explore if a particle traveling forward and backwards along the same vector experiences the same drag force. So at the top, I tell you that's what I'm testing. And I tell you a little bit more. This is in face-centered cubic aluminum. I then show you the code and explain how I did it. And then end with a simple table. I show you the stopping power forward and backwards. And I show that the difference is very small compared to those values, likely within numerical tolerances of the algorithm. And so hopefully, given that I've explained what's going on here with text, you won't need to understand how the parcel code works in order to execute these two tasks asynchronously and in parallel. But you'll be able to get the main gist of what I'm trying to demonstrate. And the idea is when I build a notebook, I build them up into these long narratives. So we'll take a look at the full version from where this came from. So here I have the notebook that Ben and I worked on doing this asymmetry calculation. You can see that I start off with an observation that in some cases I find that forward and backwards are not identical. And then I constructed a notebook to explain why that's actually valid. So going through here, I have my related work section. Here is that paragraph I demonstrated to you earlier. I compute my pattern. Then I go through and illustrate a counterexample, one where I have asymmetry. The rest of the notebook goes through and illustrates a few more examples explaining why this happens. There are cases where when I travel forward and backwards, I see the same events, but in a different order, which causes the asymmetry. So I can go through and show that visually. and be able to explain back why that happens. So in short, hopefully I've illustrated here that you can use these Jupyter notebooks as a way of being able to not only organize your own thoughts, but record them for posterity along with the actual execution of that task, so that the two are never separated from each other and your work is by construction reproducible. Now, Jupyter notebooks, like any tool, rely on you being able to both know how to use them and kind of have the tools to be able to use them effectively, or have the understanding about how they can be used effectively. So to give you an idea, here I've listed some of the common pitfalls that I've run into myself. The first of which is not actually writing that documentation. And this, if you've had some experience in software development, is one of the kind of things of being able to write well producible code. That once you've written the software, your motivation for going back and explaining how it works will have sharply dropped off. So I make sure to write my documentation or write my explanation of what I'm going to do before I do it. And this not only helps me make sure that I understand the problem before I put pen to paper, but ensures that that documentation actually happens. Additionally, Jupyter notebooks allow you to execute code interactively, which means that you can have notebooks that the first time you run them, you can change, run them again, and they may work that first time you run them, but once you have deleted the results that keep track of how you executed notebooks, say, or cells within that notebook in a different order, or changed the values and executed them again, that information is lost. So what you need to do to ensure that your notebook will still run is periodically restart that kernel and run all of the cells, which is actually hidden in the Jupyter notebook. There's under this kernel setting, I can go through into my notebook and restart and run all. We'll make sure that this notebook does what I want it to do. Now, moving forward from there, some of the other techniques that I found are, it's difficult to keep code well organized if I find I need to use the same code in multiple studies. So as I'll get into a little more details later, you can use Python's packaging mechanism to ensure that you can import different notebooks. And additionally, Jupyter notebooks don't come immediately packaged with their environment. So I use the repo to Docker standard, which I don't believe we've been using in this seminar series, but I'll briefly show you. Allows you to create notebooks or to create a set of folders that when you publish them to GitHub can be rendered as an interactive website. And I'll show you briefly what that looks like. And then finally, just because you can interleave code with text doesn't mean you will. So in order to avoid the paradigm of having code and text that are separate from each other, I try to ensure that each block of code at least has some text between it after usually about every 10 lines, effectively ensuring that my code can completely fit on the screen. So if you want some more kind of feedback on the ways you can use notebooks ineffectively, I highly recommend this talk from a few years ago from JupyterCon, where they invited someone who, as you can see by their title, does not like Jupyter notebooks. And he, in fact, goes through many of these pitfalls I've described and more that will help you explain how this tool can be used ineffectively. So a very important talk to see if you end up using Jupyter a lot in your research. So I'm also even more pedantic about how I structure my projects, knowing that I want to keep these notebooks very simple, like a paper. I want them to have a single clear idea that they communicate to others. So if I have a larger project, what I'll end up doing is splitting my notebooks into different tasks. And you can see here, I have them ordered by their execution order, so that I can easily understand that in order to run that direction-dependent study, I need to first build the machine learning model. Additionally, I take some other reusable parts of my study, like the figures, and save them in a special location, or my data sets. and place them somewhere where I can know to get them and ensure that I can publish them all later. Once I've put my notebooks all in this way, it becomes very easy for me to be able to rerun that study later. And in fact, in many cases, I will write a shell script that allows you to execute these notebooks from the command line and ensure that you can easily rerun them to ensure that you get the same results later. I do a lot of work with techniques that have a lot of randomness in them. So I constantly fret over whether I'm going to get the same result if I run it a second time. And this makes it very easy for me to test and answer that question to build confidence in the work. Now, as I mentioned earlier, one thing you can do with Python is build your own Python modules very easily. Effectively, all you have to do is create a folder with this init.py file in it. And that Python will recognize as a module that you can use those from or import statements in order to pull methods out of there. If you couple that with a setup.py file, which at minimum is the 5 or 6 lines I've illustrated here, you can use that from any of your notebooks, regardless of how you've organized your repository. So this is a common technique I use to be able to ensure that the code that I know I'm going to be reusing between many studies is stored in a way that facilitates making that easier. Another common technique I use is combining tests that I want to run many times and compiling those into a run script. So here I'm using Python's argparse module, which I can actually illustrate what that looks like in practice, because that's what I've been doing this afternoon in one of my projects. I can create a simple command line script, which will go back to my project here, where, let's see, sample stopping distances. I can create a little script where I can give it the inputs to my parameter or to my experiment that I want to run. It will execute that experiment and then save the results in a directory where I can analyze them later. You can see here, I'm currently running a study where I've varied the velocity and direction of a particle. And I've got all of my output data from that study saved in a folder such that I can go back and analyze it later with the Jupyter Notebook. So that these long-running tasks are ones that I know I'm going to want to run different times and keep those variances between each run together. This pattern allows me to do that effectively, yet still keep Jupyter Notebooks such that I can explain what the analysis pipeline for these tasks looks like. Here in this particular example, I'm computing the Bragg peak location in a material, which when I have a radiation particle, is that distance at which that particle dumps the most of its energy. And this is really good to know if you're, say, designing cancer irradiation equipment. I want to be able to understand where that radiation particle is going to release the largest amount of energy. Now, moving forward from here, we'll talk a bit and briefly about how I can take these notebooks and once I have them published, or once I have them available, immediately take that information and make it broadly accessible to others. So at this point, we've created a repository that has all of my notebooks that explain the research. It has my data sets saved in particular folders, which is especially important if you're doing machine learning related work. And I can now take that data and partition it out into other folders. And to illustrate the importance of this, I'm going to talk briefly about a study I performed back when I was a PhD student. And after getting a bunch of questions from a colleague, finding that they found different results than me, how that ended up changing my view on how publication should happen. So in this particular example, what I ended up doing was comparing a machine learning model against some baselines and then using it to find materials. And even though I published the original source code and the data, I didn't publish the full set of scripts that I used or the run files that were generated and used to write the paper. So what I ended up finding later is that even though I'm the person who allegedly did this work in the first place, I ended up getting different results when I ran the code later. Now, I actually ended up finding that my models performed better than a baseline. Instead of a 5-fold increase, it was an 8-fold increase. And I found materials that were similar, yet subtly different enough that I couldn't be able to exactly pin down how the original predictions were made. And this, even though it perhaps wasn't to the extent that I should go back and retract this paper, was something I never wanted to happen again. So the practice that I've taken to is publishing all of my data in ways, or all of my data and all of my software in ways that make them intrinsically reproducible. And some of these tools you're going to learn about later, but I'll briefly touch on the value that they provide you as a researcher. So at first, one problem I want to do is ensure that the data that I've taken time to collect and neatly organize is available in that well-organized form and easily discoverable by others. So as an example, I take my data about materials properties and make them available through a database published by a startup called Citrine Informatics that places my data in a well-structured format so people know exactly where it came from and allows me to link that data with information describing where I got it from. Additionally, I take my code from those studies, just as we had with the Jupyter notebooks, and I showed you with a demonstration earlier, make them published on GitHub, such that people can go and download and run those software. And when I publish those repositories along with the description of how that run file works, you can go through and immediately open them in Binder, such that you don't have to worry about installing the environments on your own. Binder will take care of building that for you and giving you access to Jupyter. Further, I take the exact form of the data that was used when I wrote the paper, and I publish that to a repository like the Materials Data Facility that is designed to handle this archival data, where I need to store a version that is never updated, different than GitHub, which is all about being able to modify things over time. And this allows me to ensure that you can go back from a figure and trace the exact version. And often I go through and link that repository containing the scripts directly to the Materials Data Facility publication containing the version of the scripts that I used during the study, along with all of that run data. Further, and I'm going to touch on this briefly because one of our later sections is going to describe it, I take one of the particular artifacts from machine learning studies that are interesting for others, the machine learning models I created, and publish them through Dl Hub, which, as you'll learn, allows people to access them and make predictions using those models without ever having to figure out how to install that model's dependencies or find a computational resource capable of running it. Dl Hub solves both of those problems. And as I believe KJ and Ari will be telling you, there are tools that link all of these types of publication together. A project we're working on called Foundry allows you to link data sets that are published in the Materials Data Facility and link them to the kind of machine learning models that you might want to use to analyze them. So in this way, all of the contents of a study, and here's an example done by folks who are not from UC and Argonne, can be linked together such that along with the publication, you can easily find all of the data, software, and machine learning models that were produced by it, such that you can reproduce it. Now, at this point, I'll wrap up my talk for today so we can all stay on time. But the things I want you to take home with you are to think about doing your science as if you were in Jupyter notebooks, and write those notebooks as if they were like papers or laboratory notebooks, such that once you're done with that science, it's already in a format that you can share it with others. And instead of just publishing these scripts available, make sure to publish everything. Publish the data sets in a way people can easily download and reuse them. Publish the exact run files so that you can trace a figure back to its original data, and take those machine learning models and make them available through a tool such as Dl Hub that allows them to be used by others in a way that relieves them of the burden of having to understand your Python environment. So if these are ideas that you want to incorporate in your research, I really encourage you to start using Jupyter until you get comfortable with it. It's got a bit of a learning curve. in order to figure out how to use it effectively. But hopefully I've convinced you that it's something worth doing. And if you're going to use Jupyter, go through and read this talk about why Joel Gruss doesn't like Jupyter notebooks. It's not only an excellent example of how presentations can be done in a way that makes them accessible to the crowd, but it's also something that contains a lot of great information. So at this point, we'll move on to the next presentation, but I'll be happy to answer any questions if we have a few minutes.
Great, thanks, Logan. I appreciate that talk. It was really, really well done, and I think it highlights the importance of thinking about reproducibility from the outset rather than waiting around towards the end after you've lost some of your own context, perhaps. So, putting in the work up front, I think, can save you 10 times the effort later. And I like the idea of having this template or a type of rule set that you follow to make these repositories for your analyses. And I wonder if you've thought about making a template and making it available on GitHub. Is that something that you've done?
No, I haven't. But since that came up in our a group meeting this week, it's been on a short list of things to do. Say, create a setup.py file and a data sets and figures folder that at least give you the bare bones on how to get started and sort of some guardrails to help you, or guide rails to help ensure you go in the right direction. So if I do that, I'll make sure to communicate it out to the AI for Science community.
Great. Yeah, I think that'd be really interesting. Okay, so I think we'll turn it back over to me. I'm the next speaker, so I'll share my screen again. And if somebody, oh, good, now Zoom tells me that you can see my screen. That's great. Okay, so we just heard Logan's talk. That was great. Also, just kind of rehashing the fact that the last thing I mentioned was, when is FAIR not enough? FAIR by itself, as I mentioned, is a set of guiding principles, not an implementation. We're going to talk now about some of the actual implementations that we're starting to realize. But before we get there, I want to talk a little bit about the state of the community right now. So I'll start with the good news. Data and machine learning, I think, are unquestionably becoming key drivers of scientific progress. This chart on the left shows the number of articles versus the year. And you can see sort of around 2015, 2016, you start seeing this large spike in the number of articles that are using topics of data science, machine learning, AI. And you kind of see that across all of the different major branches here of material science, chemistry, physics. And I've tracked statistics in other domains as well, and it's the same. So you see this, this new tool being deployed pretty rapidly across science with sort of astounding growth rates. Over the last 5 years, for example, material science has had a compound annual growth rate of almost 100%, which means it's doubling almost every year. So sort of astounding levels of growth. Other good news, the data ecosystem, this is for material science, but I think the story echoes true in other domains as well, that the data ecosystem of services and tools is being built and populated. So there's repositories being built, there's software to work with the data, there's places where models might be stored, like ML Exchange or DL Hub. And so all of this is starting to create this great software and data ecosystem that many of us can now use. And so it's sort of becoming a question of, how do you put these pieces together to do reproducible research? But one thing that we've seen is that, if you find a paper and you want to reproduce the results, most people are not as thorough as Logan as far as making their data and code available in a very nice package. And so you may find this great paper that you're interested in using the results from, but you may have lots of questions like, where's the code? Where are the trained models? Where's the training data? How could I actually reproduce these results? How could I use these and reproduce them and build on them? And really, without all of these pieces together, especially the code, the models, and the data, how can you make progress? And the truth is, it's often very slow, and you often start from scratch. So unfortunately, the location of many different data sets and models and processes and code that people don't publish are sort of in the trash bin. So I think we're going to talk a little bit today about the types of services that we're providing that can provide some help for this. One project is the materials data facility. So you'll hear us mentioning materials quite a bit, but we're in the process now of standing up other data facility equivalents. So we'll be bringing this to other domains. So you can imagine the way that we could scale this to other domains. And really, I think we all know that AI needs data. So MDF is working to enable simple publication and discovery and usage of data. So we work to enable publication of especially extreme scale data sets. So data sets that might come from the advanced photon source, maybe many terabytes, may come from advanced simulations that may be many terabytes, or small data, but we do support large data, and I'll describe that a little bit. We harmonize interfaces across heterogeneous data sources. So we try to index data from many places and make it available through one search index. We automate metadata extraction. So when data are published, we perform automated metadata extraction, load that into a catalog that allows you to search. We're also working to fuel machine learning for material science by collecting important community and best-in-class data sets and providing trivial access to these data sets in formats that are ready for ML usage and are self-described. And we'll talk about that as the Foundry work that Logan alluded to. We're also working to develop software and data infrastructure for automation. We'll see if we have enough time. Once we get to that section, I'll decide if we have time, but otherwise I'll make the slides available on that section. But basically, we're working to create software and tools that enable community development of automation pipelines, connecting many services, connecting, for example, work that's being done at the beamlines at the advanced photon source with the computational resources at ALCF. We're working to develop exemplar cases to show the power of this software-defined automation, and we'll talk about a couple examples there. So first, working to enable simple publication and discovery of data and usage, we have this materials data facility, as I mentioned. So briefly, researchers create or generate data here. They want to publish their data. They submit it to MDF. We collect that data. We perform a series of domain-specific metadata extractions. So for example, if we get VASP calculation, for example, we understand the structure of that data, and we can extract things like the crystal structure and many other metadata pieces that we could load into a searchable index, composition, et cetera. And so then users can come through and they can query based on all the things we automatically extract. So many locations where you publish your data, you sort of just publish and you have a zip file sitting on a repository somewhere. There's no way to sort of separate the different calculations that were done or the experiments that were done. But we try to index as much as we can, make them searchable, queryable, aggregatable, and collectible. And we also pass back to the publisher a DOI for citing data, a long-term storage location, a landing page, and essentially an API to that data set through our Python package over here. So just to give you an idea of the type of data that we've collected about 70 terabytes of materials data, representing nearing 600 data sets now, almost 1,000 published authors. You can publish via web interface where you fill in a form that describes the title, authors, where the data is located now, add some tags, et cetera. We then collect that data, perform the extractions that I mentioned, and allow you to query it. Or you can do it by script. So you can, obviously you don't want to have to fill out a form 1,000 times if you're submitting many different data sets. So you can do that with a Python script as well. We've also been piloting an email interface. So this is quite new, but just to give you an idea that we're thinking about the easiest ways to let people get their data published and out to the community. And interestingly, we've just started this beta in the last month or so with email, and about 50% of our data is now coming in this way. So it seems to be quite popular to send an email to get your data published. As I mentioned, we natively handle big data. So many other repositories kind of cap you at a couple of gigabytes of data stored. We have a distributed storage model. So we have storage space at ALCF, on the new Eagle cluster, on Petrel, and at the University of Illinois Urbana-Champaign. So we allow you to publish very large data sets. As you can see here, this researcher published a 2 terabyte data set on XCT data that they collected on cracking of a specific type of ceramic polymer. So this is data that would often be kind of sitting in a closet somewhere, and we provide mechanisms that allow you to publish that. You simply go to this DOI and you can interface with it through the standard Globus interfaces. Just to show you that's not a fluke, we've worked with this beamline at the ALS with Dula Parkinson, Natalie Larson to publish a number of their different data sets. You can see many of them are quite large, and these again are data sets that probably would have been dark to the community if not for the tools that we have now. And simply you just find the data set, they can cite it in their paper, the researchers can then go to it, grab the data and use it. We've also done this with a group at UChicago. This is an interesting data set that they've generated around discovering advanced biocompatible organic electronic materials. And they performed some really unique molecular dynamics calculations that ended up being almost 8 terabytes of data. And they reached out to us and we worked with them, and this data is now available to the community through MDF. So quite interesting that you can publish these very large data sets now. And we actually see high uptake of reuse of them as well. So as we can track the usage, we see many of these large data sets are quite unique, and people from around the world do access and use them. DL Hub is another service that Logan mentioned. DL Hub is the data and learning hub for science. And really what it is it's a simple way to find, share, publish, and run machine learning models. And we'll show a little bit of this today, but we're still working on cleaning up some aspects of this service before we make it generally available to the community. But the basic concept is that a researcher would be able to publish a model, for example, from a GitHub repository, scikit-learn model, TensorFlow, Keras, PyTorch, Python function. We collect the ML models in these common formats. We create a container for that model, register that into a model catalog, and then a researcher can come and find this in the model catalog and run it using distributed computing resources. The researcher gets back a DOI for citing the model, a landing page, ability to run it in the cloud, and an API to the model. So as Logan mentioned, instead of having to install the different software, we have this container running in the cloud that allows you to just simply send the expected inputs, and then you get the outputs back. So it's a very easy, low energy barrier usage for these ML models. And this is basically the question that we are trying to answer is, what if I want to evaluate a model from a paper? And so this is this paper from Scientific Reports, where they have this model built that allows you to look at coherent diffraction inversion using these deep generative networks. And if you wanted to reproduce this in the past, you'd have to install the software, maybe retrain the model if they didn't have the trained weights. In this case, they did a great job and had all that available, and we helped them load that model into DL Hub. And then all you need to do is simply, you have the structure model and the phase model. You load in the expected inputs, which is not shown here, but you then send that to dl.run, and you give it the inputs, and you get the intensities and phases, right? So that's essentially as hard as it is to use this model. So rather than having to poke around in their GitHub repository and go through all that pain, you can just simply run it through the API that we've defined. As I mentioned, we're looking to fuel machine learning for material science, but also other domains. So we're branching into many other domains like chemistry and biological materials and beyond. And of course, the great thing about software and data infrastructure is that it's mostly domain agnostic. And of course, there are some things that are domain specific, like the ontologies and vocabularies that you might use, but most of the other pieces are fairly domain agnostic. And so this is a slide that I saw Logan show, but I'll briefly go through it. Basically, it's combining the capabilities. This is Foundry, which combines the capabilities of the Materials Data Facility and DL Hub. And essentially what we want to do here is radically reduce the energy barrier to access these curated machine learning data sets and models. And really what you see here is we'd like to make it simple for model publishers to publish their models into DL Hub, data publishers to publish their data into MDF. And of course, what we do right now is we call these data providers and model providers. And so essentially right now, MDF and DL Hub, since they're our own projects, are the providers of choice, but we have a stack that will allow you to add other providers in the future if people adopt these capabilities. And what we really think is important is that as we build this, we see that consumers then have a very nice view into reusing these capabilities. So it doesn't take much to imagine that you import Foundry, which is our Python SDK. You perform your loading of your data here, and you run your model using the f.run. So with 4 lines of code, you've grabbed your data, you've run your model, and you've started hitting your reproducibility targets. So here is a data set for advanced energy storage material. This is a data set from Logan. I think I'll skip through this a little bit as we're getting a little bit lower on time. But basically, you can see using Foundry, you have just a few lines of code that allow you to load the data set here with just the DOI. You can then understand the contents and use the data. Sorry, I think my internet is cutting out a little bit. Sorry, can everybody still hear me okay?
Yes.
Okay, sorry about that. Okay, so anyway, you can use Foundry to load the data set using only the DOI. So if you publish the DOI, you can use that DOI to load the data, understand the contents, and run the model, load the data into RAM here, which shows you the tabular view of the data. And then once you have that, you can obviously show views of that very quickly. So just with 5 or 6 lines of code, you've got the data set ready to use. And you can imagine how that might feed into the work that Logan showed earlier. This is one that Logan showed, so I'll skip through that. But essentially, it follows the same format where you load the data using the DOI. You get some description, and then you can use the data set here. This is just to show you that you can do it with more than tabular data. So for example, this is a data set on atom position finding benchmark. And essentially you have the DOI that is associated with this data set. You load the data with the DOI. You get a description that shows you the keys, the splits, and more. This gives you an idea of the data contents and how you can use it. This gives you an idea of the splits. And of course, then with just a few more lines of code, you can use that in your Python to interact with it here and show this example that has the atom positions underneath and the atoms, which is the thing you want to predict the position of, on top. And the really nice thing about this is that it shows you the nice thing about this is that this research group at Wisconsin, Jingray Wei, Paul Voiles, and Dane Morgan, spent a lot of time collecting this data, and they spent the time annotating it, and it took them probably 6 months of effort to collect this data, but anybody who wants to use it, it only takes them a few more minutes. So it starts adding that type of asymmetry. And if you, I'm not sure if we're going to run this today, but essentially you could imagine a case where you can load a data set with just 4, 5, 6, 7 lines of code, and then you can run a model with another 3 lines of code, and you get to a point where the replicability and reuse become almost trivial. So you could really imagine the structure of Logan's notebooks, if you incorporate Foundry into it, could become much more simple. And of course, then composing complex flows of data and applied functions becomes possible. And I think we'll turn it over pretty soon here to Nikil and Ari and KJ. So Ari and KJ will be showing a number of these examples that I sort of highlighted here, but in detail, they'll run through them in notebooks and show you how those work. And I think with that, I will turn it over to Nikil. I think we'll skip the software and data infrastructure, but I'll show that in the slides that I share later. Nikil, are you available?
Yep. Hi, Ben. Can you hear me?
Yep, sounds good.
My screen. All right. So hi, everyone. My name is Nikil. I'm an undergraduate at University of Illinois, Urbana-Champaign. Today, I'll be talking about inference optimization and also how to containerize AI models. So the broad idea here is, as we learn to develop deep learning models, we want to really aim for reproducibility. And part of reproducibility is all the packages and software that you need to run a deep learning model. So you might need, PyTorch or other packages that perhaps are not installed on your system. And so containers are just a neat way to package all of these different requirements, libraries, software, and files into one so-called container. And then you can just send that container across to another person who wants to use it. And then I'll also go over inference optimization, which is the idea that if you have a trained model and it takes a long time to run on inputs, then you can just optimize the inference so that you can get like a 3x or a 5x speed up on your predictions. So that's the high level overview. So the plan is that we will basically go over the training of a simple model to classify images in CIFAR 10, which is a data set that has 10 classes. And we will task a model, we will give a model the task of, given an image, it has to predict which of those categories that image corresponds to. Then we'll take a look at how to use containers to run these models. And then finally, we'll take a look at inference optimization using TensorRT. So TensorRT is this software development kit that is developed by NVIDIA. And it's used to optimize inference time. So if you have a deep learning model that takes, for example, 20 seconds to run on inputs, if you use TensorRT, you can half the time or sometimes even 3x to 5x speed up. So that's the broad overview of what we'll be doing. So let me jump over to the code. Can you see the Jupyter notebook over here?
Yep, looks good.
Okay. So in order to get to this Jupyter notebook, you would go to ALCF, Jupyter notebook webpage, and then you would just go through the options of selecting, ThetaGPU and select the ALCF AI TP allocation, and then you should have a Jupyter notebook set up. And from the repository, from the GitHub repository, if you pull the latest code, there is this notebook called CFAR model for TRT. So that's the one we'll be using. So here, I'll go over this really broadly because what we want to do here is to take this model and then understand how we can containerize it and deploy it in TensorRT to optimize it. But I do want to go over this model so you can kind of see the whole cycle of how you might do this. So we're doing classification on CIFAR 10. So first, let's take a look at the data set. I've already downloaded the data set into this folder. So LUS Grant Projects ALCF AITP. And so you can directly use it from there. But if you do want to download it for some other reason or on your own computer, you can use this download data.py script. So initially, we define some transforms and we define our training set and our test set. So these are the classes that are available in, or that we have to classify the image. We have to classify the image as one of these classes. So let's take a look at what some sample images look like. So these are some sample images in the data set. So, and these are the ground truth labels of these images. So this is a truck, this is a plane, deer, and another plane. So this is what we would like our model to be able to predict. So having looked at the data set, let's now define a neural network model. I'm going here with a convolutional neural net, kind of a standard model that you might have seen in previous tutorials. So you have a convolution layer followed by pooling layer, followed by 3 fully connected layers. And so this neural net, we want to train this neural net to predict which class an image belongs to. So we also have to define a loss and an optimizer. So we use the cross entropy loss here and the SGD optimizer that you may have also seen from previous tutorials. And the idea here is now we train the network. So we have a training loop where we have a number of epochs and we train the network. So for the sake of time, I already have trained this network, but this would be the code to train it if you want to do it again. So I've trained the model. It's also available on the GitHub repository for 10 epochs. So it's called cfar-net 10 epochs.pth. So let me load in this model and then see what it thinks. So, these are images that are from the test set, and they have ground truth labels of cat, ship, and plane. So these are the actual labels of the images. And then we now want to see what the neural net thinks of these images. So we would say outputs equals net of images. And then we can see what the neural net thinks these images are. So here we can see it thinks cat, bird, and bird, or car, bird, and bird. So, in order to fully evaluate this model, we would have to run this neural net on the entire data set. So we can get the accuracy of the network on the entire data set of 10,000 test images. And here I also benchmark, how much time it takes. So if you use a random neural network, you'll get 9%. That's kind of, you have 10 classes, and then you are basically just guessing at random. Now let's try with the saved model. Okay, so it appears I have not saved the model properly. So, but if you look at the GitHub repository and you use the model there, you should get an accuracy of around 63% here. And that indicates that the model has actually learned something. And because this is a 10-way classification task, and therefore the model, if it predicts at random, it should get around 10% accuracy. But anything more than that, like 50 or 60%, it means it has learned something. So now the next step here is to try to optimize the inference time for this model. And in order to do that, we first export the model to this format called ONNX. ONNX stands for Open Neural Network Exchange. And it's basically a file format that allows for interoperability in machine learning models. So this is the code to export a model to ONNX. And the idea is, you have a PyTorch model and you want to convert it to some other format. So ONNX is just an intermediate format that you can use. So running this code will allow me to generate this cfar-net 10 epochs.ONNX. So what this has done is I've taken the cfar-net 10 epochs.pth and converted it to ONNX format. And the reason I'm doing this is because I want to use this ONNX file to convert the model to TensorRT. And what that will allow me to do is to run the models much faster. So whereas a model might take 10 seconds to run initially, we would be able to run it in 5 or less seconds. So that's the broad idea. Going back quickly to my slides, how do we actually run these models? So the idea is that we are on a cluster, and we might not always have the software and packages that we need installed. So this is where the idea of containers comes in. So what is a container? A container allows you to create and run that allow you to package up pieces of software in a way that is portable and reproducible. Right. So why might you use containers? You might use them because they encourage reproducibility and ease of use of code. So let's say you have a deep learning model that you trained on system A, and then you want to run the deep learning model easily on system B. the packages and software that were present on system A might not be present on system B. And so if you could package it up somehow, using this idea called a container, then you could easily, run the model on system B. So some popular container platforms include Singularity and Docker. And I'll give you a brief overview of how you might use a Singularity container. So one way you could do it is to download an existing container from a library. But you could also convert one from one format to another. So if you have a Docker container, then you could convert it to a Singularity container, for example. Or you can build a container from scratch using a definition file. So here's an example of a definition file. You can see that you have this bootstrap and from sections, and these are called the headers of the definition file. And basically what they tell us, or what you specify to Singularity using these pieces of information, is what the base operating system should be. So here it's Ubuntu. And then the way you would specify what software you want in your container is in this post section. So here you can see I've said apt get install fortune, cause, and lolcat. So these three are kind of popular packages. lolcat is something you may have seen a picture of a cow on a terminal. It's kind of a popular way to introduce terminal to users. So this is just kind of a way to show how you can install different packages into your container. If you have this definition file, then all you need to do is Singularity build lolcow.sif. SIF stands for Singularity image format. And then you would specify the definition file, which we have here, which is called lolcow.def. So here I have a terminal that I've opened, and all I've done here is I've loaded a module. So Conda 2021-1130, and I've activated the module, and I've navigated to this folder, LUS Grand Projects ALCF AI, and this is all on the GitHub repository. So what I'm going to do here is I'm going to see if I can open my Singularity image. So this file right here, trt-torch-new.sif, that is my container that I've already created using the method that I just described. So the idea is we want to open this container and run our model on the container. So there's a few commands to do that. So you would first want to start a Singularity instance. So the command to do this is Singularity instance start, and then you specify the name of your container, and you specify the name. In this case, I already have it, so it says it already exists. But when you run it the first time, you will be able to avoid that one. So now the next command that I need is to open a shell where I can interact with the container. So I would say Singularity shell --nv and instance TensorRT. And doing this will open up a Singularity shell. So this is a place where I can have access to all the software that I installed from the definition file. So we are inside the container now. So the idea here is, now that we are inside the container, we would like to run the models that we have. So you can see if I run this cfar script torch.py within this container, it runs perfectly well, and it gives me an accuracy of 63%. So cfar script torch.py just has the code that I showed in the notebook for evaluating the model. And I'm able to run it perfectly fine on a terminal, without worrying about what environment, what software, what packages I have, and so on. So this is basically the broad idea of a container. You want to go inside the container and then run the models that you have, and you don't need to worry about packages or software or libraries. The final thing I want to show you is how to optimize these models using TensorRT. So TensorRT is an SDK or software development kit for high performance deep learning inference that enables low latency and high throughput for deep learning inference applications. Basically, what this means is if you have a deep learning model that takes a long time to run, you can run it through TensorRT. You can use TensorRT to reduce the inference time. So this is a trained model that you have already, like the one we have now. And if it takes n seconds to run on your input data set, it's very beneficial if you can run it in n over 3 seconds or n over 10 seconds. So this is particularly useful in applications that involve deploying your models on the edge, or models where you need quick inference time. So this is a really good tool to be able to do that. The broad idea behind TensorRT is this thing called reduced precision. The high-level overview is neural networks usually represent their data using float 64, float 32. And if you can reduce this bit width, then you'll basically be able to run your neural net faster because it has to do less multiplication. And so by reducing the precision of your neural network layers, and also a bunch of other techniques, such as dynamic tensor memory, so efficient use of tensors in memory, you will be able to reduce inference time. So let me show you what the time using TensorRT looks like. So here you can see I have Python 3 CFAR script torch.py, which is the original torch model. And that takes around 3.6 seconds to run. The accuracy of the network is 63%. But if I use the TensorRT model, which is the CFAR script trt.py, it takes only 1.5 seconds. So that's a significant speed up. And by adjusting the batch size that you use and other parameters, you will be able to push down this inference time even further potentially. There is one potential downside here, which is that the accuracy might go down. So here you can see the accuracy that the TensorRT model has achieved is 56%. So it's a trade-off. So if you want higher or faster inference time, then you might want to consider using TensorRT. But the cost that you might have to pay is slightly less accuracy. But depending on your application, that might be useful to you. So yeah, this is what I wanted to say. Thank you, and I can take any questions.
Great. Thanks, Nikil. I'll maybe we'll save the questions for the end, but I see there are a couple questions in the Slack if you want to take a look there and perhaps answer some of those. But with that, I will turn it over to Ari and KJ.
All right, thank you, Ben. Thank you, Nikil, and thank you, Logan, for presenting earlier. My name is Ari. Hello, everybody. I'm one of the primary developers of Foundry, which Ben and Logan introduced earlier, and I also contribute to DL Hub. And so today we're going to be, me and KJ are going to be presenting how to use Foundry and DL Hub to load data sets, as well as how to use DL Hub to run models. So let me just share my screen with you all. Okay, so today, at first, I will demonstrate using Foundry to load data sets that we have stored, and KJ will do the same. So first things first, we're going to be running these in Google Colab. So for anyone who hasn't used Collab before, basically it'll run notebooks like a Jupyter notebook in the cloud, which is nice for distributed resources. And so in order to do that, all you need to do is go to the AI Science Training Series repository, click on the notebook that we're going to share and go through, copy the URL. And then if you go to collabresearch.google.com, in the GitHub tab, you can directly enter the link and open the notebook here. And so then it'll open it in Google Colab And this is nice because it just has a distributed environment. And so you don't have to deal with installing things on your local machine. So now that that's established, I want to go through and show you all how to load some atom position finding data. So Ben and Logan had both kind of referenced this data set earlier. This is a data set that was put together by Jingray Wei at the University of Wisconsin with Dane Morgan and Paul Voiles. And the purpose of the data set is to train a machine learning model to find the positions of atoms in images of them. So what we're going to do is, and the interesting thing about this data set is also that it's an Hdf5 data set. So for those who aren't familiar, Hdf5 is a hierarchical file format that is used to encode usually heterogeneous data. So this is nice because it has both image data in it as well as metadata, JSON metadata. So first, I'm just going to do some basic setup, which just checks if you're in Google Colab or if you're running the notebook locally. You are also welcome to run these locally. So if you feel more comfortable running them, for instance, on ThetaGPU or something like that, you're more than welcome to. And I'm going to skip over these installs because I already installed everything before this presentation, but all you have to do is install Foundry and Matplotlib. And just as a quick refresher, since it's been a long session today, Foundry kind of combines the best powers of the Materials Data Facility, MDF, and DL Hub, so that you have dataset capability and model capability all wrapped in one package. Right now for Foundry, model capability is still in production. So we're still working on that, but the dataset capability is fully deployed and available for use. So now let's import Foundry. I just gave a little refresher. And so to instantiate Foundry, you need a Globus account. We have linked right in the tutorial to the page to set up a Globus account. So if you go to login, you'll be able to sign up. And as Ben mentioned, you can just use your university email. And so now let's establish. We instantiate Foundry. And for this data set, we're going to refer to it using a dataset DOI, which is nice. You can also use like a human readable name. But for this one, we'll use the DOI. And when you download the data set, you get this nice kind of summary, this programmatic summary of what's in it, which is nice for just, you know, I can't tell you how many times I've downloaded a data set and I'm like, what's actually in here? This is just a nice overview. So we can see that within the Hdf5 format, we have these different keys, which are kind of like dataset columns. And we have images that are available. We have that are labeled, or unlabeled rather. And then we have raw images that haven't been processed yet that are unlabeled. And we have metadata that describe the experimental conditions under which the data were captured. And we have the coordinates for labeled atoms. So we can see that these first three, the images, raw data, and metadata, are meant to be used as input to a machine learning model if you want to train a machine learning model, and the coordinates are the target. And we can see here we have about 299 items, and we provide some associated metadata such as like the type of task. In this case, this is a supervised learning task, as well as the domain, which is material science. So here we just kind of peek at the data itself. We can see that this is an Hdf5 object with the different keys that we've previously listed above. And so now we're just going to break these out so that we can easily visualize the data using Matplotlib. And so as you can see, this is what the data look like. These are the atoms, and then the drawn dots are the positions that were grabbed. And so using this data set, somebody could easily train a machine learning model. As Ben had mentioned, it took Jingray like 6+ months to assemble this. And now in, you know, just a minute, if not less, I was able to run through and quickly visualize the data and get a sense of what it looks like so I could then train my own model. So that's our atom position finding notebook. I will demonstrate one more data set notebook today. And then KJ will do the others. So this notebook was put together with our collaborators at Northwestern, University of Chicago, and I believe Argonne. And the goal of this project is to find dendrites in examples of metals, so like the dendrites of metals that move into other metals, and the difference between those. So the goal of this notebook is to build a predictive UNet model on that data, and then create an augmented data set to use with the model. Yes, so we will go through. And so again, I'm just kind of doing the basic setup of establishing, and these things are just to establish for Foundry whether or not you're using Globus, for example, whether or not you're running in Collab, stuff like that. I'll skip over the installs because I've already done this beforehand. We make sure everything is nice and imported. And then just like before, with this one line of code, we instantiate Foundry. Great. And then we're going to load the segmentation data set. And so similar to the atom finding data set, we get some metadata about the data set so that we know kind of what's in it. We can see that this just has one input set. It's called a split of unlabeled images and then the target of labeled images. And they have kindly, when they published this data set, they noted that it was an unsupervised learning task and a segmentation task. And so then we're just going to go, and now the data is downloaded, actually load it into local variables. And so that's what we've done here with our inputs and outputs. And this is just a quick visualization of what the inputs and outputs look like, what the targets look like. So you can see here, these are the dendrites. These are the masks, which is nice. And so now we're just going to do some setup for the model itself. I'm just going to kind of skim over this because that's not the main focus today. This is just a summary of the architecture of the model. Here we go. And so here we can see, once again, now that we have kind of taken a peek at the images, what the original, the ground truth, and what the difference between them is. And then we're going to augment our data. So right now we only have 30 images. We want to extend that because that is not enough for model training. And so we've augmented the images here by doing some distortion. So here you can see that it was kind of rotated and squished and sheared a little bit. And so that is just to help our model get a better semantic understanding of what the dendrites look like. And so I'm going to skip the model training process because it's a little longer, but I've already run the training and have a pre-trained model saved. So I'm just going to load that. Fantastic. And so now we run our predictions and we can see the performance. So if this was the original, this is the ground truth, we can see the prediction and the difference between the two, which is kind of fun. And so that was just a quick example of kind of how you can use Foundry to quickly load and understand complex data sets and then work with them right out of the box, which is nice. And so now I'm going to pass over to KJ, who has two other examples to show you, and then we'll come back to me and I'll show you some of our model running procedures.
Thanks, Ari. I'm KJ, and like Ari said, we are both developers on Foundry. I have two examples to show you. So Ari ran her notebooks in Google Collab. I ran my notebooks locally before joining this meeting, just because my computer does not love when I try to run notebooks and share my screen at the same time. So these should all work for you both locally and in Collab, but I'll just be walking through this now. So I'll start with this zeolite data set. We also have in each of the notebooks, or in some of the notebooks, we link to papers for the data set. So if you're interested in any of these, you can find more information in these notebooks. So in this notebook, we'll be instantiating and authenticating Foundry, just like we saw Ari do, although we'll be doing it locally instead of in the cloud. We'll be aggregating data from the OSDB, and we'll be just performing some basic data exploration. So this is the cell that detects your environment. So we're local, so it'll set some variables that we'll use when instantiating Foundry. We've got environment set up, and we'll be importing a few packages. We'll be using pandas to work with the data. We'll be using Matplotlib and Seaborn for our data visualizations, which we'll do at the end. But for now, we can get into importing Foundry and instantiating Foundry with those variables that we set above. And then we'll be loading the data, which we'll be using the DOI for this data set. But as I mentioned before, you can also use a short name, which we'll be doing in the next example that I'll show you. So once you've loaded the data, you can see that a little bit more information about it. So you can see all of the keys with their different types, either input or target, got descriptions for each of these. We're pulling from the training split. You can see this is tabular data, the task type, short name, domain, the number of items, all of that just when you load the data. And then we will be loading our data from that train split, our inputs into X and our targets into Y. And once we've done that, we can take a look at what X looks like, our inputs, and you can see that all of the keys that we saw that were type input above are now these column headers here, and we can see the first 5 entries. And we can do the same thing with Y. These are our targets, the same keys that were type target above, and then just the first 5 entries here. So I'll explore the data a little bit. We'll be exploring the template for this compound here and making this plot that is showing the phase competition metrics of this template versus other zeolites. And then we've got another plot that we've made down here. And so these plots, the authors generated in the paper that's linked above, and we were easily able to regenerate these plots, which was pretty cool. So I'll move on to our other notebook example. This is band gap data. Oops, let's get back to the beginning. So in here, so for the band gap data set, we'll be instantiating on authenticating Foundry locally, aggregating data from 2 data sets this time, and then we'll be building a predictive model. So we've got these environment variables, our install statements if you're in Google Collab, and then importing. So we'll just be using Matplotlib for visualization, scikit-learn for the model, and then pandas and NumPy for working with the data. So we just need to import Foundry and then instantiate Foundry with those variables we set in that very first cell. And then we'll load the first data set. So this data set, we're using its short name. And we're loading from the train split as well. So you can see these keys with their type input. So this has mostly type input, just one type target. Tabular data, yeah, all of this, and items. And then we'll be loading our second data set also with the short name and also from that train split. And we can see we've got the same keys as above with the same type, input, our one target down here, the same data type, which is important because we'll be concatenating these data sets. And once we've done that, we can see our inputs are in that X variable, which we can see them all here, all the keys that were type input. And then our Y, just our one key that was type target and the first 5 there. So now we'll be pulling out composition data that'll serve as our targets. That's just taking a subset of Y, which we chose 300 here. And we can take a look at our Y subset, our first 5 and last 5 entries there. And then we'll choose other features that we can use in training in the cell here. And then we'll be creating our model. So we're going to be creating a grid search model. And then we'll be using a random forest regressor as our estimator. And then we're going to perform cross-validation and scoring to ensure that the error values are below the desired thresholds, which we can see here. And then finally, we'll be making this plot to see how our model is doing. And so this plot shows the mean absolute error, and you can, as you can see here, our model is not doing well right now, but that's okay. We actually have an open challenge for this notebook. Like we said, all of our notebooks are on the Foundry repo, and we have that linked in the repo for this talk as well. If you want to create a pull request with edits to this notebook that have a model that's performing better than ours, we would love to see it. So I'll go ahead and pass it back to Ari. I know she's got more to demo for DL Hub.
All right, thank you, KJ. Yeah, so that was our dataset functionality. And as KJ mentioned, all of those notebooks are available in the AI Science Training Series repository, as well as in our Foundry examples repo, which are linked in the Google Doc that we dropped in Slack. And so now I'm going to demonstrate how to run models in DL Hub. We currently don't have this notebook available for use because we're still making some improvements to DL Hub right now. But we're planning to release everything to the community very shortly, which is exciting. So I'm going to share my screen again. Okay. And so earlier we talked a bunch about the atom position finding data set. So I thought it would be suitable to show you all what that train model looks like when we run it in DL Hub. And so once we do very similar things that we had to do before. So we're going to run the little intro cell to set up our variables. And we would install DL Hub. I'm going to skip over this because we've already done this for you. When we import everything. And so very similar. So this is, again, the model that was built on that atom finding data set that we showed earlier. And so what we're going to do is we're going to just prepare some basic inputs to the model. So I have numpyified this test image, and that's going to be our image used in inference. So the goal is going to be to find, to get back the positions, the coordinates from the model of where the atoms actually are in this image. And in addition to passing in the test image, we also pass in some metadata associated with running it so that we can tell DL Hub basically what we need. So for this particular one, we want to use these specific Gaussian weights, or excuse me, these specific model weights. We don't want to use CUDA, things like that. And so now if I visualize, this is the image that we're using for inference. So we're going to pass this to the model that's currently in DL Hub. And this kind of connects to Nikil's presentation in that DL Hub is built on repo to Docker, which kind of Dockerizes everything, and on funcX, which is really fun. So and that allows us to have distributed, federated running of containers. And so underneath everything, this works by having containers within the DL Hub namespace that will run as you need them, which is fantastic. So now we're going to run the model. And so currently this is executing on a server at the University of Chicago on River. But we have the option to change that to meet users' needs in the future. And now we can see that we get back the results, and these are all of the, yes, these are the results for where the atoms are in the image that we just provided, which is fantastic. So now too, just so like for reference, this is what the training data look like. So we trained the model on this. I loaded this here with Foundry and just these few lines of code. And then we ran inference on this. And that's just a basic quick run through of how to run models with DL Hub. If you want to publish a model, I have a quick script to just kind of demonstrate what that looks like. So publishing a model with the DL Hub Sdk is relatively straightforward. There's a little bit of setup because you need to tell DL Hub, okay, who are the authors, like what are the inputs, things like that. But it's really well documented. Logan did a fantastic job documenting that out. And yeah, so all you would really need to do to publish a model like the atom finding model through DL Hub is have your function that you want to run. So in this case, we run Inference, which is just a helper function for this model running function over here. And then we tell DL Hub via the, we have different classes in DL Hub where you can specify what kind of model your model is. So that way we can handle it most appropriately. And so one option is to have a model that is encapsulated within a Python function. And so that's what we're doing here. So this function is called Inference. And so we set up a function pointer to Inference and tell DL Hub, okay, this will be our model to run. And the other nice thing about DL Hub is it doesn't have to be a like machine learning model. It could be any Python function. So even if you wanted to run like a simple, even a simple hello world, you could do something like that. So we tell it that this is where our function is. We set a name. This is the short name kind of KJ was referring to earlier for data sets. We have a similar functionality within a DL Hub for models. And you add a requirements txt to define the computational environment. This would also accept other kinds of environment files, environment defining files, such as a conda environment.yaml file. You tell it what inputs it would expect. And so here we describe an input of an image and as well as the predictive properties. And you tell DL Hub like what the outputs will be. And so this helps the user of DL Hub understand how to run your model. You add all the necessary files for running your model. And then we have a nice schema validator to make sure that to catch yourself in case perhaps you miss something. And then you publish it just with this one line right here. And you'll get back a task ID telling you that the job was received. And then when it is, when it is completed, you're able to find your model over here in dlhub.org, which is fantastic. So currently we're still working on making some improvements at DL Hub right now, but we are just about done. And I'm going to stop sharing. Okay, thank you. Yeah, looking forward to releasing that to the scientific community coming up soon. So I'm going to pass it back to Ben now.
Great. Thank you, Ari and KJ and Nikil. Very nice presentations overall. I think really starting to show how you can imagine reproducibility in the different scientific domains coming together with the software and tools that not only that we're building, but many other teams are building. So actually we're exactly on time. That's amazing. So we have 15 minutes set aside for questions. I know there were a few in Slack, but I think they were mostly answered. Does anybody have questions here? I'm not sure, do we need to promote people or do people need to raise their hands or something? I'm not sure what if you want to ask a question, unmute yourself. That'd be awesome. I'll check the Slack.
Everyone should have access to their audio, so.
Okay. Rachel asks if the Slack channel will still be accessible after the series ends, and Taylor says yes. So that is good. I think one thing that we plan to be doing over the next few months is really engaging with with the ALCF community and others to start populating the Foundry with different data sets and models and all of that, because it's great if you can start with more than just a few. So we're really excited to start working with you. If you have data sets or models, come talk to us. I think all of our emails will probably be available through the slides that we share. But you should be able to find us with our names as well. We're all at UChicago or Argonne.
If there are no questions, we can of course end the Zoom session. And if people have any follow-ups, feel free to write them in the Slack and we will get notifications.
Yeah, I have a quick question. I think somebody replied to my question by referring to funcX. Can you say a little bit more about what that is?
Sure. So funcX, if you're familiar with Globus, the way they define storage endpoints, funcX is very analogous in terms of a compute endpoint. So you run and you install and run a client on a specific compute location, and that gives you access to, or that allows you to run functions as a service through that endpoint. And so with DL Hub and Foundry, since Foundry is built on top of DL Hub, essentially when you run a model, you define the endpoint that you want that to run on. If you don't define where it runs on our default location, which is a small computing allocation on the UChicago River cluster. But if you do define it and you have, like we've set up endpoints on Theta, ThetaG, then you can run that on much larger resources if you want to do a large inference batch or something.
Thank you.